Hello friends, today's question. A tuning fork of 512 Hz is used to produce resonance in a resonance tube experiment. The level of the water at the first resonance is 30.7 cm and at second resonance is 63.2 cm. The error in calculating the velocity of the sound is. So this question is quite straightforward. We know that the velocity of the sound is 330 in the normal medium, 330, and we are going to calculate the velocity of the sound based on the level of resonance first and second using the tuning fork frequency, and we are going to subtract them, so we are going to get that error in calculating the velocity of the sound. So let us start from there only. So we know that first of all we try to understand the resonance. Understanding resonance, and this is resonance with respect to resonance tube. Understanding resonance with respect to resonance tube. So the difference in it is given that the level of water at first resonance is 30.7 and at second resonance is 63.2. So difference in these two resonance, that is the first and second resonance, will be always equal to lambda by 2. Okay, so this is the basic, you can say, criteria for in case of a resonance tube. The difference between the first and second resonance is lambda by 2. We say the difference between the first and second and second resonance lengths corresponds to half wavelength of the sound wave. Corresponds to half the wavelength of the sound wave. So based on this explanation or description, we will able to find out what will be the wavelength of the in the water, and based on this we can find out the, we can say, velocity, because velocity is equal to frequency multiplied by lambda. Frequency is given to us, and this description is going to help us to find out the wavelength. So we are given that first resonance length let us suppose that is L1, that will be equal to our lambda by 4, and second resonance length let us suppose that L2, and this will be equal to 3 lambda by 4. So like I said, difference between the two you can say lengths will be equal to lambda by 2. So therefore you can write L2 minus L1 will be equal to lambda by 2, and from here I can write my lambda will equal to twice L2 minus L1. And in the question, L2 and L1 are given to us, So I simply substitute the value. I get lambda will be equal to twice L2 is our 63.2 minus L1 is our 30.7. So this gives us lambda will be equal to 0.65 meters. So we are able to find out lambda. Now we can find the velocity. Velocity of sound, let us call it V. V will be equal to frequency multiplied by lambda. Frequency is given as 512 Hertz. Lambda we just found out 0.65. So this gives us that our V will be equal to 32.8 meter per second. So this is the observed value of the velocity of sound in the water. But actual value of velocity of sound is 330 meter per second. So you can say this is observed value, but actual value of velocity of sound let us call that Vs, which will be equal to 330 meter per second, and this is observed value, so let us equate that V0. So therefore we can say error will be equal to 332.8 minus 330, and that will be coming as 2.8 meter per second, and that will be equal to 280 centimeter per second. So therefore the option number D is the correct option. So you can say option D is correct. Option D is correct. Now the same question can be asked in a little bit different way also, and in this case we can say if the error arises in the measurement of the lens, it means the error is in the measurement of L1 and the error is in the measurement of L2, what will be the error in the measurement of the velocity of the sound? Okay. So we can just you can say modify. So we can say if the water, or we can say if the error arises due to the propagation. Okay. You can say if error arises due to the measurement of L1 and L2. Measurement of L1 and L2. So the value of L1 and L2, this is L2 is 63.2 and L1 is 30.7. It means both the measurement, that is L1 and L2, will be having an uncertainty of plus minus 0.01 centimeter. So from here we can say for both lengths means L1 and L2, the measurement uncertainty will be, let us suppose that is delta L, and delta L will be equal to plus minus 0.1 centimeters. Okay, because the values are given with respect to one place decimal, so the uncertainty will be only also because of the plus minus 0.1 centimeters. So from here we can find out the uncertainty in the wavelength. You can say uncertainty in wavelength, let us call that delta lambda will be equal to twice, and we have delta L1 plus delta L2, and this will be giving us 2.1 plus 0.1, so we get delta L will be equal to 0.4 centimeter, or we can write this as 0.004 meters. And from here we can find out the fractional uncertainty. So we can say fractional uncertainty in wavelength. This will be equal to delta lambda divided by lambda, and we get this as 0.004 divided by 0.65, which we have already calculated. Okay, we already calculated lambda, so we use same lambda here also. Now we can find out the fractional uncertainty in the velocity of the sound. Fractional uncertainty in the velocity of sound, and obviously that will be delta V divided by V, and that will be equal to delta lambda divided by lambda. So we can say our delta V will be equal to V multiplied by delta lambda by lambda. V we already calculated is our 32.8 multiplied by 0.004 divided by 0.65, and this comes approximately equal to 2.05 meter per second. Or we can say plus minus. So if there is a measurement uncertainty in the length L1 and L2, so this will be our with respect to the velocity. So same question can be asked a little bit in a different way. So this completes the question. Thank you.